Hello! We're going to do a video about hyperbolic trig functions. It's an introductory video and we're just going to start with how we define the hyperbolic trig functions sine and cosine. Now, the really weird part about hyperbolic trig functions is they're not trig functions. See, this function here that is outlined by the black curve, in between its two asymptotes there, that's not a trig function at all, but it's called a hyperbolic sine. Its actual definition is e to the x minus e to the minus x over 2. And because it's a hyperbolic and we call it a trig, well, we need to give it a name that kind of displays that. So we call it sine hx, but saying that is really hard, so its nickname is sinh at x. So this is sinh at x. It's a little different than an x cubed, as you can see, or even another curve that you can think of, such as an exponential or maybe an x squared. See, there's a bit of an inflection happening there, which you don't see with x squared. So enjoy that. Hyperbolic cosine is very similar. It is e to the x plus e to the minus x over 2. So the only difference here is the plus sign. And as you can see, at 0 it's 1. By plugging in x equals 0 we get that. And it has this asymptotic strange behavior in between the curves as outlined in green here. So why are these called trig functions when they're not called trig functions? This sinh, and then of course we call this cosh because it's a lot easier to say than cos of x, right? So what we'll do is we'll just take a quick look. If you take a look, I'm just going to squeeze on in here, the sinh of 0 is 0. And that's something that sine has in common with this function. At the same time, cosh at 0 is, as we discussed, equal to 1. So it looks as if these functions kind of share some properties of trig functions, and it doesn't stop there. As a matter of fact, if you look and you evaluate cosh squared at any x minus sinh squared at any x, then you get 1. And that's pretty similar to the Pythagorean identity that we use in trig. Now, if you were to divide this identity here on the last line by sinh squared, you would get another identity that looks very similar to one you know from trig. Same if you were to divide both sides by cosh squared. So these are kind of parent hyperbolic functions, and when you use them, like trig, they almost fool you into thinking they're trig, except little tiny changes like this minus sign, for example. So we don't do too much with hyperbolic trig in our classroom. But the reason why it's motivational for us is because, as a matter of fact, hyperbolic cosine is a very good model for a very common object. I'll try to see if you can think about it while I'm stalling, but without you having even a hint, it's hard to tell. Yes, there are some buildings that are structured around this type of mathematical shape. However, when we look in a moving car at power lines, you'll see that power lines in between their two poles, they do sink. They're never pulled strictly taut like this thing that I just did. They're not straight, parallel to the ground, right? They kind of have a sink to them. And as a matter of fact, they're not parabolic. They don't look like any power function, but if you want to model them using a shape, the way they naturally rest just due to their weight and due to gravity, and due to the fact that they're attached at certain distances from each other with poles, they look most like cosh of x. So I thought that would be a nice little thing to mention, but I don't want to get too carried away, removing the tips off my markers and so forth. What I would like to do is, I'll invite you to stop here if you want, no problems there. What I'm going to do is I'm going to find an inverse function for the hyperbolic sine. We took some time in class to look at the function sine of x, which is trig, and then we found its inverse, and we had to restrict it to be 1 to 1. But see, this is already 1 to 1. Now is a good time to familiarize yourself with what a 1 to 1 function is in case you're not sure because you forget. So this is a 1 to 1 function right here. Passes the horizontal line test. So what I'm going to do is I'll take a bit of a break here to spray my board down because it doesn't understand erasing. And then just go ahead and speed up the, so that you can meet me when I start again, because I'm going to take another board and we're going to work together to find the inverse of sinh of x using its definition with the e's. There we go, that's nice. Also, it is Saturday, so I am dressing down, in case you're wondering, just in case that it is Saturday, I promise. We're not at work. That's right, we're doing math on a Saturday night. Oh my goodness. And now everyone's gonna know. All right, so we're gonna start to find the inverse by reminding ourselves that sinh of x is, and we're gonna call it y, equal to e to the x minus e to the minus x over 2. Now, what I like to do is I like to solve for x, but I know some of you like to switch the roles of x and y. That's fine. Why don't you do that now if you're following along, or maybe try it later your way. But bear with me, I don't do that quite yet. I just try to solve for x. So right here, I'll start by just getting the 2y out on the left-hand side, and that's going to equal e to the x minus, e to the minus x. Here's where I ran into a problem. I'm going to tell you plain and simple. I thought, well, maybe if I factor out an e to the minus x, it'll make something so that I can deal with it better. But honestly, at this point, we have x's stuck up on the exponent, so you're going to have to use your most favoritist inverse function ever, which is the logarithm function. It's going to be the log base e, because we have e's as the base to the exponent functions here. And then we're going to call it ln, remember? But the problem is that I can't take ln of something minus something. It won't break up, it won't simplify. There's no rule for that. Remember your 3 rules? None of those is going to help us deal with that. Maybe if they were multiplied or divided, but they are not, and there's no way to make them such. Without getting rid of that minus sign, we have a problem. So what we're going to do, we're just going to do a trick. And you're going to times e to the x. I can't believe I said that. Multiply by e to the x. That looks horrible. Okay, so there. This is my multiplication thing. Times e to the x, everything in the equation. And you make it more complicated, it ends up looking like this. 2y e to the x equals e to the 2x minus 1. Take a minute to figure out why. If you're not sure, you just go through and you multiply by e to the x, each of these terms on your own. Now, at this point, we need to still try to isolate x. And what you need to see is that this is kind of supposed to look like a trinomial, except it's not in x, it's in e to the x's. See, this is a quadratic term because it's squared, and then this is like the linear term, except it's e to the x, not x, and then that's the constant term. Ooh. So you end up getting something that looks like 0 is equal to e to the 2x minus 2y e to the 2x minus 1. And really, you have to kind of see, as I said, this is kind of like the x squared or something squared. And then this is, that's just, that, I don't know why that 2's there. Go away 2. You're not wanted here, right? So then this is just e to the x. This is like the x term and then the constant term. So in order to solve this, you'd have to factor it out or use the quadratic formula. When you try to factor it out, it doesn't quite work as nice. So try the quadratic formula. And if you don't like the way that it looks, just kind of let e to the x be a w for now and get w squared minus 2yw minus 1, where w is going to be the variable of your trinomial. Give it a pause now. See if you can use the quadratic formula in order to get the two roots to this equation. And from there, we should be able to take a couple more steps using the natural log in order to get our inverse function. Gross, right? It's gross. As long as you agree, looks like you know what you're doing. So if you just want to see the punchline, what I'm going to do is I'm going to show you that w, or e to the x, right, is going to equal, so w equals e to the x is equal to, what do we get? We got 1 y plus or minus, I thought it was a 1, but it was a y, that's why I tripped over my words there, y squared plus 1. That's after a little bit of simplifying, but not too much. And out of the quadratic formula, we get two roots, which often happens. Problem is, if you want an inverse function for something, you can't have plus and minus whatever, because an inverse function is going to be a rule that's going to assign something unique out of this. And if I plug in y's or x's or whatever, I'm not going to get anything unique out of this. I'll get two possibilities. So we need to choose a root. And it turns out that it's the positive root that you choose. Maybe we could think about why. Can you imagine how when we had sinh, it kind of looked like this sort of, I don't know, SE shapes? Oh, wow. That's a new low for me. But see, you could have values of y which are really, really high up here. So say y is really high up and it happens to be greater than 1. Well, if you were to put y greater than 1 in order to track it back to an x, like an inverse function does, then you put 1 minus, and then here you get 1 plus 1, so you get 1 minus root 2, which is negative. So it's the positive root. So we choose e to the x is equal to the positive root. That's y plus root y squared plus 1. That's the x. So you've gotten it down to just one little x. It's just stuck in an e. So you basically can take the natural log of both sides in order to get the expression that you want. But I ran out of room. But I don't want to take your time up and erase the whole thing, so I'm just going to erase part of it. Especially this. This must go. Okay, you're almost done. In fact, you probably know what to do already, so what you can do is you can just shut her off and finish and conclude, or hang in there and wait for us to do it together. So the idea is if e to the x is this, the argument that we stated to get rid of the negative possibility, then we're going to take the ln of both sides in the last little bit over here. So we're going to go ln of e to the x is equal to ln of y plus the square root of y squared plus 1. And you know what? You might have a y here, an x here, and an x here. That makes it easier for you at this point. Ln of x and e to the x being inverses gives us just an x on the left-hand side. And we end up getting the expression ln of y plus the square root of y squared plus 1. Not a nice labeling for an inverse function, so we'll conclude by saying therefore f inverse of x, or y inverse, because we called it y. There's y, e to the x minus e to the minus x over 2, and it has inverse ln of x plus the square root of x squared plus 1. So your relabeling gets you that. So your hyperbolic sign, because it's made out of e's, ends up having an inverse that's made of lns. And the same thing would happen with the hyperbolic cosine. If you want to try it, you can. A hint for you is you'd have to restrict the domain first. Do you remember cosine, how it looks like a bowl? Or cosh, not cosine, hyperbolic cosine. Well, if it looks like a bowl, then it's not 1 to 1. So give it a try if you want. It's just practice with algebra and logs and inverse functions. It's a good one to try on your own. If you have questions, let me know. That was a good long video. Thanks for your patience.